Phone on the caddy, make sure it's in there. All right, today we have a couple new things to talk about. We are starting the next section. I will give you time today to work on your page 7 if you would like to finish it. I did send an email this morning reminding people of what the homework is. Okay, homework's due tomorrow. Book cover's due tomorrow. So I think it was really early this morning. It's probably normal. That's probably a little bit earlier than normal. It just had some time this morning to make sure I can send out that email. Just make sure that gets taken care of. Tomorrow, book covers, I'm going to check that right when you walk in, so don't wait till the end of class. Okay, question.
Did we get some work time today or not?
Yeah,
I wasn't paying attention.
I wonder if that's it. All right, so let's talk about growth and decay today. There's a couple different things I want to discuss today, and it's a part of the questions that we had in the homework. Because I had somebody ask, hey, where are you going to cover this? Come sit, Brown, before I kick you out. So, okay, exponential growth. That's what exponential growth looks like. It's a curve, right? It's not linear anymore. We're on a basic curve. Now, here's the idea. Typically, on exponential growth, when the spacing is equal, the growth will be constant or continuous. Okay, it's not going to suddenly change directions. Okay, so the growth itself will have a multiplier, and how you can tell that is when you look at the data to see how the data is falling. Okay, I'm going to show you some different calculations today to calculate whether it's got a certain type of growth, if it's actually exponential or if it just appears to be. But exponential growth, true exponential growth, the actual growth will be continuous, it will continue to grow like this, but the growth will be constant the entire time from beginning to end. It'll be the same exact growth percent every time. Even though it looks like it's getting taller, it's because it's growing by that same rate and there's bigger numbers. It's kind of like the idea of like rabbits. You have one rabbit, they multiply, and it keeps going, and then eventually it just looks like it explodes in population. Because there's more rabbits, obviously, you have a lot more, but then the growth rate is still the same, so more rabbits having more rabbits just explodes. It's like the idea of like The Walking Dead, right? If you ever watched that TV show, The Walking Dead, where in the actual show itself, like it was one day they had an outbreak, and it was 3 months later, US is pretty much taken over, and we're pretty much done as a country. It was like, that type of growth was exponential. Because if you think about it, one person gets bit, then that affects 2 affects 4, and it just keeps going and it grows faster and faster and faster until the population is covered in like a 2-week period. So that's the concept of it. So its time frame is it's significantly shorter than you think it is in terms of that show. But that's that idea, I like the concept of that, that's what this kind of represents. Question?
You kind of just spoiled the show for us.
Spoilers. So, all right, now let's talk about the actual numbers itself now. So exponentials, there's 2 types of growths when you actually look at it. So let me give you this. So here's an amount. I'm going to call this A naught. That's how you pronounce it, A naught, or it's a little like, it's a subscript 0. Then we have some type of rate, and you have a time on it. Okay? This type of idea on growth, it's I think in previous years you might have seen it as PRT or something like that. That's something that you might have seen in like a pre-calc class. What this is the amount that you're gaining over time. This is the initial amount. Initial means starting, but it's called A naught. That's just how it's pronounced.
Bless you.
Bless you. But A naught, that's how it's pronounced. And then R is the rate. Now here's the thing. On the rate itself, here's how you know if it's growing or shrinking. Growth or decay. If the R in that case is bigger than 1, it's growing. If it's less than 1, it's shrinking. That's the concept.
You guys write this down.
Yeah, and then time here being years. Time, years, preferably. Okay, but again, growth is for any number bigger than 1. So larger than 1. You can assume that the other direction would be shrinking. That's the first type. Exponential growth. This is like, what you're actually looking here, this is a type of exponential form. It's got some variable to power on it. There's the natural number of growth, where it's, they use different letters, but I'm gonna use the same letter. E is the natural number. E represents a compound interest kind of a thing. We talked about that last year in pre-calc. How it's actually found is taking like rate in your time and actually dividing it and then adding it to 1 and putting it to that same power and t, where it's growing, where this growth rate is like this weird magic number. It happens in nature, that's why they call it the natural number. It's like 2.71, blah, blah, blah. It's a irrational number, but it happens because of compound interest. And it's just this number that grows. It's this number is basically how bacteria infects the body, or how the population explodes in terms of growth rate. It affects everything because 1 affects 2, 2 affects 4. It's that same concept, and it grows. And why it's not a perfect number, why it's not just doubling, is because you still have death, you have mortality that you still have to deal with, and other natural circumstances. So it like balances itself out. It's kind of this weird thing, but do you notice that the formulas kind of look the same? The book uses different letters than I do, so that they like use Q's and P's, but you get the idea.
What's a K?
K is, okay, so that's a good question. So again, this E represents a natural number. K, this number, is the actual growth percent. It's the actual decimal for that growth. So if it's growing by 3%, it's 0.03, right? If it's, doubling, they'll put a 2 there. It's the actual growth that's taking place. T is still time. So now, how do you know if, in this case, whether it's shrinking or not? It's whether the K number is positive. It will have growth if the number for K is bigger than 0, larger than 0. So even if it's like 0.02, that's growing by 2%, it's growing. If it was negative 0.02, then it's shrinking by 2%. That can happen as well. Okay, do we understand the differences here? Like between the two formulas? Okay, let's talk about like an example here. That's a good way to put one. All right, so I'm going to use population. Let's say we have population growth. Okay, and I'm not going to use the E. I'm just going to use like we're on a constant growth for a city. They're not actually putting exponentials. So let's say the initial population of Garner is 6,000 people. I'll just say a nice clean number. So that's my A naught number. That's my initial amount of people. Okay, that's my initial. And R is some type of rate. Let's say that the population of Garner is growing by, let's say it's 0.5%, not even 1%, 0.5%. So this is what 0.5% would look like in terms of growth. Now, why I put a 1 in front? You still have the entire population plus an extra 0.5% after it. So you're doing the whole population plus you're growing by half, 0.005. And then we're going to go for 3 years. This will tell you the amount of people after 3 years. If you had that constant growth happening from year to year to year to year. If it was staying consistent. Okay? So, if you type these in, again, if you have a calculator and you want to type the numbers in, how I would do this, I would calculate this part first. You have to actually type in 1.005. You have to type the little caret key, then type in the 3. Now, if you don't have the little caret key like my calculators do, you can, maybe there's like a little X to the Y key, or Y to the X key, or maybe you have just like a Casio where they just have the little boxes where you can fill in the boxes itself.
That's what I have.
There's just a lot of different forms. But once you type that in, this will give you, some number of probably around 1, somewhere in that ballpark. So 1.005 to the third power. It's this number, once I type this in, turned out to be 1.015. And there was more numbers after it, but that's roughly what it was. And then we're going to take that times 6,000. And this will tell me my population after 3 years. Now, using the exact decimal, there's more decimals back here, but using the number that my calculator represented, I'm getting about, after 3 years, 6,090 people. Okay. That's the idea, right? In terms of growth, it's actually pretty close to what Garner's predicted to be in a 5-year period, not a 3-year period. We're expected to grow about 100 people.
But do you
in
think
5
we
years.
grow that much?
No, Garner's school district is, so I mean, it could be Ventura, it could be Garner, it could be, but they have projected numbers that they use for the state. But yeah, so this can give you what the amount will be after 3 years. Does that make sense how like the formula's working? Now, the formula I actually used was this one. Right, typed in my rate, typed in time, typed in my a to the 0. That's the idea. So now, let's say that I didn't know my initial amount of people, okay? I didn't know it, okay? But I have data from the past few years, okay? So, let me give you this example. This is something that's very similar to what the book does to like really compare numbers. All right, so let me type in some stuff here. Let's see. Just want to make sure my numbers are somewhat accurate. Okay, so here's my data. So I don't know my initial amount of people, and I don't even know my rate, but I know after the fourth year, my population is 4,363.78. Okay, if that makes any sense to you. After year 5. .79. I don't even know my initial, I don't know my rate. That was year 5. And year 8. So they didn't do a census every year, they just took some data over, a certain time frame. Blah, 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 blah. There's more numbers, obviously. Now, here's the weird thing. Okay. Even with these numbers, I have year 4, year 5, year 8 from the initial population. I don't even know what the initial population was. I have all this data that they provide me. I can actually tell you by looking at this data whether it's actually exponential growth, like real exponential growth. Whether there was one set initial number, whether its growth was constant and continuous. We can actually find that out by just seeing what year we're testing and what the numbers are, like the actual population. And we can actually check. Now how this works, it's using a common sense idea of looking at the percent. So what they do is they do this. Because how do you find percent? You divide numbers, right? So if I took A0, R to the 5th power, and I divided by A0, R to the 4th power, right? I divide these. What happens to A to the 0? They would cancel, right? Because a normal division, like terms would cancel out top and bottom. What happens to the R's if I divide those?
It just becomes R.
Becomes R to the 1st power, right? Because they would literally cancel. It's the same, in theory, if these are the same rates of growth, the R's would cancel out to be 1. R to the 1st. That's 5 over 4. You cancel like a normal division in Algebra 2 class. It's called the cancellation method for exponents. Then over here, the 5th year number was 445979. And I'm going to divide that by 436378. And when you divide these, this will actually give you a percent of rate. It'll give you your growth rate. That's the percent of growth they went from one year to another year. That's just common sense, right? When you divide, it actually gives you a percent, right? That's how you do it on test scores, right? You look at your score over the total, you divide it, and it gives you a percent, what you did. So I'm going to divide these. 4459.79 divided by 4363.78. It's telling me my growth rate, I'm just going to round this number, 0.022. So what type of growth am I getting? What does that number represent? What type of percent?
2.2.
Exactly. This is 2.2% growth. It's the full population plus 2% extra. Now, to check whether that data is actually true, because that's going from here to here. it grew by 2%, 2.2%, technically. To check whether that works again, you could do it one more time to these. Do the exact same math I just did. And you can check whether this is constant growth, whether it's an actual exponential, or if it's just random data that's been pulled. That you could, this is like looking at a table, and I'm checking whether it's doing something like this, or whether it's actually staying constant and it's actually working. Whether it's actually growing by 2% every year. So that's what I'm checking for. So I'm checking if it's truly exponential, and then we can talk about domain and range here in a minute, because that was a question I had yesterday. So, to check whether you have real growth, I'm going to check from year 5 to year 8. So I'm going to divide those. I'm going to do the exact same math. A0, r to the 8, divided by A0, r to the 5th. What's your 8's numbers? 4, 7, 6, 0, 6, 5, 9. 4, 4, 5, 9, 0.7. All right, I'm going to divide these. What happens to a to the 0? Cancel these. What happens to these r's? R to the third. Now, do you agree that's not a 1? Agreed? Let's get r to the third power. Okay, I'm going to divide these numbers over here. So 4760.659, divide that by 4459.79. I'm getting 1.06746. No, I'm not done yet. Okay, and there's more numbers on that. Okay. Now, do you agree that that r is not r to the first?
Mm-hmm.
So it's not truly representing my rate, r to the first, in year 1. It's representing growth over 3 years. How do you get rid of a 3 if it's in a power? You take a cube root. Cube root is how you get rid of a power. If you take the cube root of 0.06746, that will put it r to the first, and take the cube root of both sides. If I actually take the cube root, how do you take the cube root on a calculator? You use your little power rule, your little exponent rule, and you put it like this. You put the exponent in the power of a 1/3, if you don't have that button. So how I would put something to the 1/3 power, again, I would use the little caret key. So type in the little caret, put a parenthesis, put 1 divided by 3, and close that parenthesis. But I'll put a 1/3 in its power. So, I'm going to do that. Put that to the 1 divided by 3 in the power. And here's what I'm getting. My rate. So, here's my question. You saw the rate from year 8 to year 5. You saw the rate from year 4 to 5. Is this constant growth? That's exponential. It's that second graph I showed you earlier. Because you're actually looking at the rate. You're looking at something like this. It's actually real data. It's not just random numbers that are going up and down constantly. So constant continuous growth. This type of growth is called concave up. Concave up is like bold upwards. It's growing constantly, consistently, continuously. That's what real exponential growth is. Okay, do you guys get the idea of what exponential is, though? The concept. Now, this is probably new to you. I don't think we've ever attempted something like this before, in either pre-calc or anything. It was just something that, it's just common sense, like when you divide, you get percents. I thought that was kind of a clever way to do it. What we're going to talk about tomorrow is doing the same calculations for growth and decay, but we're going to do logarithms. So you will need a calculator tomorrow. We're going to talk about, how do you figure out a growth? How do you figure out decay? If I gave you an amount, I gave you, what you're growing to. If you wanted to find a constant, if you want to know what would happen in year 50 down the road, that's what we're going to be looking at. But this is the first day to show, consistent growth, like what it actually represents, like the real math behind the scenes. Okay, now, one of the questions yesterday, and this is my last thing today. One of the questions I had yesterday was, how do you know what domain and range is? Because domain and range, over a linear or even a curve, domain and range are x numbers versus y numbers. So, domain would go from here to here. This would be domain. It's all your x numbers. How I would like you to put answers, if you're showing me actual domain, is put it in interval notation. So, let's say it went from 1 to 9, right? Let's say that that's what your data was saying. So your domain would be this, the lowest number to the highest number. Now, if there's open circles or arrows, you'd use a parenthesis. Since this has closed circles, there's an actual dot here, there's no arrow, you'd actually use brackets. Do we see the difference? That's domain. If you wanted range, range is going from here to there. That's range. So that's maybe 1 up to, let's say, 5. So then range would go from 1 to 5. Now, if there's any open circles, you use a parenthesis instead of a bracket. If there's any arrows, you use a parenthesis instead of a bracket. Okay, questions at all about domain and range? That was one of the questions I had yesterday. It was something I wanted to bring up today because it was part of exponentials as well. Okay, any other questions about the intro section? Yeah, and this isn't like in-depth notes, it's just like an intro, like what we're getting ourselves into soon. Okay, we're done for the day. You can work on your assignment, your page 7. Tomorrow we're going to continue on with this exponential idea, but we'll do like carbon dating. We're going to look at if you have an infection rate of a disease. We'll look at stuff that we did kind of in pre-calc, but instead of doing this kind of weird shortcut stuff, we're going to do stuff with actual calculators, logarithms.